Welcome everyone to today's webinar. So we are now restarting our new season on robust optimization webinars with the great speakers. So we have a joint presentation of Dike and Hertog and Thodoris Koukouvinos. So Dike and Hertog is a professor of operation research in the University of Amsterdam. His research interest is overall on perspective analysis, mainly on linear and nonlinear optimization, with the focus on a robust optimization, also machine learning and the interaction between optimization and machine learning. He's also one of the scientific director of Analytic for Better World, and he's doing a lot on that direction. And Thodoris is a PhD student, a fourth-year PhD student at MIT, an Operation Research Center, who's supervised by Dimitris Bertsimas. And today they are going to talk about their new method that they developed and its application for robust optimization. So without further ado, the mic and the screen is yours.
Thanks a lot, Reza, for the introduction, and also thanks for the invitation to speak here. Thanks also for making Row alive again. That's great. So this is indeed the topic, a novel approach for a broad class of non-convex optimization problems. But I will also show you how these ideas can be used for robust optimization. And I think that also these tools, these techniques that we will show you this afternoon can also be very valuable in robust optimization. So I will do part 1, and Thodoris will do part 2. So part 1 is about, so the total method is called RPT. I will do part 1 on RPT, reformulation, perspectification techniques, and Thodoris will do part 2 about branch and bound. So these are the authors. So besides Thodoris and myself, it is Trevor Sen, Dike de Moor, and Dimitris Bertsimas. Okay, so the link with robust optimization is the following. So if we talk about robust optimization, then we typically have to deal with these type of constraints. So we have an inequality constraint. X is the optimization variable. Z is the uncertain parameter. And we enforce that the constraint holds for all Z, for all scenarios in an uncertainty set, capital Z. So that basically means that if it holds for the worst case, then it also holds for this one. So we have to find the maximum over the set, capital Z, with respect to the uncertain parameter Z. So we have to maximize this function. Well, there are several options for f. For example, if f is linear or concave in the uncertain parameter set, then we can do it exactly by using French duality, because then we have a nice problem. If it is concave in z, then maximizing a function is easy. And we can then follow this approach that we wrote down in this paper. When f is convex in z, and that happens more often, then, in fact, there is already a paper where we used the RPT approach that I would like to sketch here. You can use the RPT approach to get an approximation for this effective approximation for this constraint. Today, we also talk about the branch and bound. In fact, Thodoris will do that. So that means that, in fact, the branch and bound that Thodoris will present can also be used for this type of robust constraints, and then we get an exact solution. And also in cases where we have a function f that is neither convex nor concave in Z, then we can use this RPT and branch and bound approach that we are going to describe to get exact solutions. The method that we will present can also be used for adaptive robust optimization. For example, we can now use all kinds of non-linear decision rules. And then by using the approach that we will present this afternoon, we can solve the resulting robust optimization problems. And with respect to distributional robust optimization, finally you can reformulate that to a robust non-linear optimization problem. So you can also use the RPT branch and bound approach for these type of problems. So what we do today is in fact an appetizer for robust optimization, and Dike, the more, will give a road talk in November on the application to robust optimization. So today is about the non-robust situation, and this is the outline. So first I will describe the RPT method by using a very small toy problem. Then I will describe how to apply it to a generic class of problems. Then I will special attention to multiplying basic conic constraints, and then finally numerical experiments. And then I will give the floor to Thodoris. So first, RPT for a toy problem. So let us, before we do that, a short introduction to RPT, reformulation linearization technique. Consists of two steps, reformulation and linearization. So RLT is already known since 1990, introduced by Shirley and Adams, and improved by many other authors, many other papers. So RLT, it's called. And RPT is in fact an extension of that. So let us start with this simple example. Only two variables. We have constraints here that are convex, one linear constraint, one non-linear constraint, and the objective here, this is a linear part, this is a quadratic part, it's not convex, and also this part is not convex. So the red part is the bad part. So if we apply RLT to this, then of course the first problem is that we can't handle this. But if we skip that problem for a moment, and RLT will in fact introduce a new variable for x1 times x2, and let's call it u12, and then they multiply the constraints with each other, and then also replace the quadratic terms by the linear terms. And by doing that, you get better connection between, let's say, the old x variables and the new u variables. And so that's in fact what RLT is doing. It's multiply the constraint with each other, but in fact RLT can only handle the first constraint. So they cannot work with the second one. So we use the first constraint and we multiply it with itself. So we get 1 minus x1 minus x2 squared greater than or equal to 0. And if you write it down, then in fact we get this expression here. And then what we do is we substitute the quadratic terms by the linear terms, which we could call u. So then in fact what we get is this is minus 5u12. And we get for this constraint here, we get u11 plus u22 plus 2 times u12, and so on, greater than or equal to 0. But here you see we get for the u12, we get a lower bound, while we are minimizing minus u12. So, you know, there is no bound on it. So that means that in fact, what we get here is minus infinity for RLT. So we now show that if we use RPT, which is an extension, we do get finite bounds and better bounds. So that's the objective value that RLT obtains in this case. Okay, so RPT, what we do here, we are also able in RPT to multiply non-linear convex constraints. So we also use the second one here. Multiplying constraint with other, thereby getting more connection between the x and the u variables, and that helps a lot in the approximation. Moreover, we can also convexify this term. So that's in fact what we will show now. Okay, so we multiply the linear constraints with the non-linear constraints. This one times this one. So that's in fact this constraint here. So here we have a product of a linear term times an exponential term. And then, yeah, what to do with these red terms, because that is not convex. Well, what we do is the following. For example, the objective that is not convex, but it is linear times convex. And so it is x1 plus 2, that's linear, times minus log x1 plus 2, that's convex. For this term, we do then the following. We multiply the argument by this linear term. So we get x1 plus 2 squared. Then we get x1 squared here. And we replace that also by the new u variable u11. And what we observe now is that this numerator is linear in the old variable x1 and the new variable. So minus log is convex. We divide here by x1 plus 2. We multiply by x1 plus 2. So this is the perspective function of the function minus log. And the perspective function is well known that that's also convex. So now by doing this trick, it was linear times convex. We multiply the argument by x1 and divide by x1. And then in a numerator, we linearize all quadratic terms. And then we get, in fact, a function that is the perspective function of a convex function minus log. Okay, the same we can do with this function, this constraint here. So let's take only the first part to show you, and then the second part goes in the same way. So what we do is we multiply the argument x1, we multiply it by this linear term, and we divide it by this term. So we get in numerator some quadratic terms. We replace that by the new variable u, and then we get x to the power linear, and we divide the argument by this and we multiply it. So it's a perspective function, and the perspective of a convex function is convex again. So this function is jointly convex in x and u. So we can do that for the other term in the same way. So finally, what we get is if we do all the calculations correctly, then we replace it, and then we get this problem here as an approximation. It's an approximation, an outer approximation, but it is convex. All the terms are convex. And if you solve this problem, then in fact what you get is this as a lower bound and this as an upper bound. Indeed, so it helps here to the extension of RPT helps a lot here. Of course, you can do also more because from this equality, we can also deduce this LMI here, that is a standard. And if we add that to this problem here, the RPT approximation, if we add the LMI to that, then finally we get that the lower bound equals the upper bound. And so that means that, in fact, we have obtained the optimal solution already. Okay, so that is RPT on a very small toy problem. And the extension is that we can now multiply also nonlinear inequalities. And we can handle more types of non-convexity. To be more precise, in fact, what is a very basic class of functions here that we can handle this type of functions, namely the sum of linear times convex functions, SLC as we call it. So that plays a very important role, the sum of linear times convex. If we multiply, for example, a linear constraint times a convex function, we also get a linear times convex function. So the sum of linear times convex function is a core class of functions that we'll study here. So we assume that the constraints are such that and the objective are the sum of linear times convex, and that we also have constraints that are convex, and for example, linear constraints and also convex constraints, so hx is convex. Okay, so what here are some examples of linear times convex functions. Of course, quadratic is also such a type of a linear times convex, but many other examples for that. And also functions that are the difference of convex functions can be formulated as such. So the difference of convex functions is a very rich class. It's in fact defined for the first time, I think, by Hartmann in 1959, and he showed that this is a very rich class. In fact, he showed that every function that is twicely continuously differentiable can be written as the difference of convex functions. So if we have that, and the functions are proper closed convex, then in fact the double conjugate of that function is the function itself. And so the double conjugate is the conjugate of the conjugate. And the definition of that is here. So the supremum of x transpose y minus the conjugate function. And if we plugged it in here, if we substitute it, we then get this inequality here, C0 minus x transpose y plus C1 star. That's equal to 0. And since we have a less than sign here and an inf here, we can delete the inf and we get these inequalities here. So this is convex, this is convex, this is the only non-convex term, but now we have linear times convex, effect linear times linear. So this is again in the format of what we want. So this is a trick to get difference of convex functions into the format of linear times convex. Okay, so that is a rich class, the sum of linear times convex. So this is the core idea now. I showed it already on the toy example. So if we have such a function, the sum of linear times convex, then in fact what we do is we multiply the argument by that linear expression. So we multiply it by qi minus di transpose x. We divide it by qi minus di transpose x, and then we linearize the numerator. And so we get here, instead of x transpose, we get a u. Now what we see is that ci is convex. The numerator is linear in x and u. We divide by the linear expression the same as that we multiply. So this is in fact the perspective function of the convex function ci, and that is convex, jointly convex in x and u. So this is a convex approximation. So that's basically the trick that we use. So we get, if you are minimizing, we get an outer approximation, so we get a lower bound. But if we solve the resulting problem, we also get values for x and also for u. So we also get candidate solutions that we can plug in and see what are the values for that. And if they are feasible, then in fact, we also get lower, we also get upper bounds. We are minimizing. We might also try to improve the candidate solutions by a local solver to get better upper bounds. So that's in fact what you also do. Great. Okay, so that is in fact the basic idea. So the format, the class of functions that plays a role is the sum of linear times convex. Those arise already maybe in the formulation itself, or when we multiply linear constraints by convex constraints, we also get linear times convex. So that's an important class. And what we do is a very simple trick, namely we multiply the argument by the linear term, divide it by the same linear term, and then we replace in a numerator, we replace the quadratic terms by the new variable u. And then we get a convex function. This is based on the fact that the perspective function of a convex function is a convex function. And the perspective is just the function itself, and we divide the argument by a linear term and we multiply it by a linear term. That is the perspective function. Okay, so what can we do? We already showed that if we multiply a linear constraint by a convex constraint, we can make it convex. But what if we multiply another basic conic constraint by another conic constraint? For example, if we have an exponential cone constraint, and we multiplied it by another exponential cone constraint, or a power conic constraint. So that's in fact what we also did. So we looked at the 5 basic conic constraints that we have, 5 basic cones: the linear cone, conic quadratic cone, the power cone, the exponential cone, and the SDP cone. And we looked at all possible multiplications. So in total, there are 15 possible multiplications. So we also studied all those 15. Some of them are already studied in a literature. For example, linear times linear by the RLT community, or linear times conic quadratic. But others are new, and especially where the power cone and the exponential cone are included. So this is finally the telephone book, as Dimitri is calling it, where we have all the 15 cases and all the possible results that we get, and here the references. So it's already in the literature, then we refer to the paper, and those cases that are new are in the paper. And just to show you that we really did all the 15 cases. Okay, I give just one example, a very simple example. So suppose that we have the exponential cone inequality, and we multiply 2 of those exponential cone inequalities with each other. So this one here and this one. So if we multiply that, for example, this one times this one, we get x1 times x4 is greater than or equal to, and multiply this one and this one, x2 times x5. And then I already divide this by x5 and multiply by x5, also for the others. And now I replace those quadratic terms by the new variable. So what I get is u14 is greater than u25 exp u35 divided by u25, and also plus u26, and so on, also for the others. And so this is a very easy example. The other examples are a little bit more difficult, but just to show you how it works and what we have done. Okay, so this is about the multiplying the basic conic constraints. By the way, maybe it's nice to mention here that there are some possibilities here where there is best reformulation. For example, if we multiply the quadratic times the power constraints, then there are many possibilities to do that. And in fact, we formulated a robust optimization problem itself to find the best reformulation. So that's already a robust optimization problem in itself. And so that is a nice nice case. So there's this case here, here, and here. So we use robust optimization to find the best reformulation. Okay, so finally, a numerical experiment. My favorite example, Dike height. Maybe you know that in the past I did a big project for the Dutch government on Dike height optimization. And when we were doing this research, I immediately recognized that, in fact, that problem also had an objective that is the sum of linear times convex already. So we took that problem, so this is the problem. So x is the variable here. Those are the heightenings at certain moments of time. X is the amount of heightening, and h is the height up to now. So h is in fact the sum of all the heightenings up to now. So don't look at all the symbols, but you know it's important to see that here, this part is this variable and this variable is linear times convex. And here, so these are just this data. So this is convex in HK, and this is also convex in HK. So this is fine. But this term is not convex, but it is linear times convex. And we have constraints here, and a linear constraints. So we can use RPT for this case. So we perspectify this term here. We multiply the constraint with each other, and we also add the LMI to it, the SDP. And then in fact, for all cases, so each row is a case, so in different Dike ring area or a different timing strategy. So we get the optimum value, so the lower bound equals the upper bound, so that's then the optimal solution for all the cases. And we also use Baron. Baron was also able to find the optimal solution, although sometimes it took more than an hour. So we stopped that to really guarantee or verify that this is the optimal solution. So these problems, they have variables in total, I think, if you x and h in total, I think number of variables, something like 40. So in this case, RPT was able to find the optimal solution. However, that is not always the case. And therefore, if the lower bound does not equal the upper bound, then we need the branch and bound, the spatial branch and bound technique. And that is exactly the method that Thodoris will talk about. But before that, maybe there is a few minutes time to answer some questions. Michael.
Hi, thank you for your talk. So yeah, I have a question. It seems to me that the linear factors need to be non-constant in your approach, right? Otherwise the difference of two convex functions is obviously an example of.
Very sharp. I think I. Yes, sorry, I forgot to mention that. Indeed, yeah. So if the functions, so the sum of linear times convex, if the function is non-linear, then indeed this factor should be non-negative. And if it is linear, then we don't have that, because if it's linear, then it's quadratic, and then we get a linear function. So that's not a problem anymore. But you know, we do get it. For example, if we multiply a linear constraint by another convex constraint, then automatically we have that this is greater or equal to 0. Does that answer your question?
Yeah, I think it does. I have to digest it, but I think yes.
Yeah. Other questions? If not, then I think
there's one question in the chat. Mark L. Stone asks, how well does RPT-SDP work on BMI?
On BMI? Oh, by matrix.
I'm not 100% sure what BMI is.
So Mark, can you explain what BMI is? Yeah, bilinear matrix inequality. Well, in fact, to be honest, I don't know exactly, because at this moment we are trying that together with other people.
And maybe a short question for me. So everything you're doing is always, you have this product of two variables, which you replace by these uij variables. So is everything possible when you have products of 3? So you could, in this case, have convex functions concatenated with a quadratic one. So when you do your trick, then you get a cubic formulation inside of your function, I think.
Yeah, that is possible. We haven't done that, and that's because, you know, that's because already now, in that's I think the disadvantage of this method is that the number of variables is squared, because we do x transpose, and so to go even further, I don't see much value in that. Maybe you can prove something theoretical, and that if you continue like this, then maybe it converges to convex hull or so, but from a practical point of view, I don't see value in that.
Okay, thanks.
Okay, so then I stop sharing and give the floor to Thodoris.
Okay. Right. Hi, everyone. Thanks for the invitation to talk in the webinar. It's a really pleasure for me. And today I will talk about part 2 of our method. which is our novel algorithm for a broad class of non-convex optimization problems. So basically what I'm going to talk about is mostly the branch and bound part of the method, since Dike really talked about the RPT part. So we have this generic formulation of a problem, which of course can be the RC of a robust optimization problem, in which we are trying to solve over the uncertain parameters so that we can reformulate our problem. So the generic problem format is that we have an SLC objective and SLC constraints, as well as additional linear constraints and convex constraints encoded in the set X here. So our goal is to try and find the global optimal solution of this problem. So just to give you some examples. So one example that can also arise in robust optimization is a non-convex quadratic optimization problem, in which case we have the SLC function sum of linear times linear. And this can happen, for example, in robust optimization and also in adaptive optimization. So as you can see in the constraint here, we can have this term R of Z transpose Y of Z, in which case, if we assume that both R of Z and Y of Z are affine in Z, then we obtain an SLC function, which is actually a non-convex quadratic. So computing the robust counterpart of this constraint here boils down to solving problem 1, in which case we have the problem of maximizing a non-convex quadratic objective over possible linear convex constraints in the set Z here. Another example is convex maximization. So assuming that we have a convex proper and closed function f, so using the biconjugate trick, we can write it as this, and as Dike illustrated earlier. So starting from a convex maximization problem, we transform it in this bilinear problem, in which case we can apply our RPT approach, since our function is sum of linear times convex. Some examples include the sum of max of linear terms maximization, in which case we are maximizing over x the sum of the maximum of the linear functions of x, in which case after the biconjugate, the problem is formulated in this form here, in which we have a bilinear objective over linear and convex constraints. Another example is Euclidean norm maximization, in which case we have maximized the norm of x. And again, using the biconjugate, we can write it as maximizing this bilinear objective over linear and convex constraints. So, for example, this can occur in a problem in which we have a second order cone constraint, and when we're trying to compute the robust counterpart, we would have a problem like this that we want to solve, assuming that the constraint is conic quadratic in the uncertain parameters Z. And finally, we have the log sum X maximization problem, in which case, again, applying the biconjugate trick, we obtain a problem that fits in our generic problem formulation, meaning that we have an SLC objective over linear and convex constraints. Now, as Dike mentioned earlier, so what we do in RPT is that we linearize products of variables with new variables. So whenever we have the product xi times xj, we linearize it with new variables uij. So ideally, we would want, when we solve our problem, we would want to have u being equal to xx transpose, in which case we would be at our optimal solution. But often this is not the case. So basically, when we solve the problem with RPT, we obtain our solution x star u star, as well as a lower bound. But because this equality does not hold, we're not at the optimal solution in many cases. So what we want to do in this paper here is try to close this gap by applying the branch and bound method to further cut the feasible region, so that we are getting a smaller region where this holds. So what we are really trying to do, what we are thinking about is how to generate, of course, hyperplanes, how to cut the feasible region and things like that. So our motivation is this. So when we solve the problem, we get a solution with x star and u star. We notice that if u star is different than x star transpose, then those vectors u star I over x star I will, of course, be different. But if we were at the optimal solution, those would all be the same. Now, further, we have this lemma here in which we proved that under some conditions on the constraints, those vectors, u star I over x star I, will be feasible for our problem. So what this means is that those vectors will be inside the feasible region, and of course they will be different, but all of them will be inside the feasible region. So since they're feasible, of course, we can obtain an upper bound. So we can look at those vectors and see which one gives us the best upper bound and keep it as our upper bound. Now, we also want, so of course, what we want to do is we want to close the gap. So we propose generating hyperplanes by leveraging the structure of this problem. So since we know that these points x u star I over x star I are inside the feasible region and they are different, so what we do is that we generate a hyperplane that separates these points by further cutting the feasible region. So so yeah, this is pretty much what we do. And we further require that the hyperplane also passes from the analytic center of the feasible region. So assume that this is our feasible region. These red dots are those vectors that are feasible somewhere inside here. And by generating such a hyperplane, we then solve the problem with RPT again on the left and right part. And we ideally hope that in one of the two cases, we arrive at the optimal solution. So we get new vectors that are all the same. But if this is not the case, we can apply this step again and further cut the feasible region in order to try and achieve it. Okay, so what we seek is a hyperplane encoded in this form here that partitions our feasible region into new regions. And this is the left part, and this is the right part, as defined exactly by this hyperplane intersecting with our feasible region. So the way that we generate the hyperplane is actually by solving an optimization problem and adding what I discussed earlier as requirements, as constraints. So we will want our hyperplane to separate those vectors xi, u. And what we do is that we use binary variables, zi, to encode in which side of the hyperplane its point I is. Further require that the hyperplane passes from the analytic center of the feasible region. And finally, we require that it is of maximum margin, meaning that it maximizes distance from those points. So putting it all together, we arrive at this optimization problem here, in which we solve over F and L, and also which encode the hyperplane. So the hyperplane is defined by all vectors x that satisfy F transpose x equal to L. So, and of course, yes, we have the binary variables z that encode in which side of the hyperplane each point is. So we solve this problem in order to generate a hyperplane to further cut our feasible region, and then in each part solve the problem with RPT again, trying to obtain the global optimal solution. Okay, so these were the main parts of our method. And here we say that under some further conditions, we have established convergence of our method, the global optimal solution of our problem. So briefly, the extra conditions are that after some point, if we no longer generate hyperplanes as I described earlier, but we generate them in this form here by computing the range of the feasible region, then in this case, assuming further that the functions are limited continuous, then our method converges to the global optimal solution of problem 1. Okay, before going to the example, what I really want to mention is that, of course, as you see, our method requires a lot of computation. So, of course, the way that we're generating the hyperplanes, that we're solving a mixed integer optimization problem, we're computing the analytic center. But our real benefit is that we don't have to do this a lot. But as we will show in the numerical experiments, we can generate very few of those hyperplanes and solve the problem fast. So even though that we have a lot of computations, we can really solve problems fast in this way. Okay, so we illustrate the method on this toy problem here. So we have this SLC objective over the linear times the exponential terms, as well as some linear and some additional convex constraints. Okay, so we started the root node here, and we solved the problem with RPT, as Dike illustrated earlier. And we get this optimal solution here, X, which gives us a lower bound. And we also look at the candidate vectors, which give us an upper bound. So we see that we have a lower bound and an upper bound, which are quite close, but they are not matching exactly. So we apply a first step of our method. So we generate the analytic center of the current physical region, and we generate those two hyperplanes, as you see in the left and right arrows here. So on the right part, we already get a node with a lower bound greater than the upper bound on the left part, so we stop there. At the left part, however, we see that we get in bounds that are closer. So we add one more hyperplane here. And as you can see, finally, at the left part of the second, at the second branch, on the second step of our method, we were able to locate the global optimal solution of our problem. So we get this vector X here, which is the global optimal solution, and we get a matrix U, satisfying U being equal to XX transpose. Okay, so as we have seen how the method works on this toy problem, we now go through our numerical experiments of the paper. So the first numerical experiment that we consider is maximizing the sum of matched linear terms over linear constraints and an additional convex constraint. So we use the biconjugate reformulation of this problem. So we obtain the problem at the right part over X and Y. So what we did, we multiply constraints here, it's time. And whenever we generate a hyperplane, we add it as an additional linear constraint here, and we multiply it again with everything. So in fact, so generating a hyperplane gives us a lot of inequalities that really help RPT improve the bounds. So in the left plot here, we look at our results for 5 instances, and we look at the computational times of our method compared to Baron and Mosek for solving this problem. And as you can see, for instances 2, 3, and 5, our approach really has an edge over these methods, meaning that it can solve the problem much faster. And in many cases, can also solve really at the root node or generating very few hyperplanes. And at the right part, you see that, of course, all methods find the optimal solution, but the difference is that Baron, for example, in some cases cannot prove optimality within the time limit of 1 hour. The next experiment is the log sum maximization, in which, in this case, we have again a convex objective. And using the biconjugate trick that we have mentioned, we obtain this bilinear objective over linear constraints. So again, we apply RPT with the branch and bound, and we see that again here, in some cases, our approach performs better than the state-of-the-art methods for solving this problem. And here, in addition to the previous experiment, there were a few cases where our method found the global optimal solution, where Baron did not locate the exact optimal solution within 1 hour. And we obtained something a little less optimal. So the next one is the non-convex quadratic optimization problem. So we have a non-convex quadratic objective over non-convex quadratic constraints. And in some cases, we also have some additional linear constraints in our problem. And as you can see here in instances 4 and 5, again, our method was able to solve the problem very fast. So actually, in all 8 instances considered, our method could solve the problem really fast. With instances 4 and 5 also having a difference with Baron, where it didn't solve the problem within 1 hour. And in all cases, of course, it identified the optimal solution, but did not prove optimality within 1 hour. So the final problem that I'm going to talk about is the robust palatable Dike problem, something that we worked on very early. in an extension of our work. So this the robust palatable diet problem is an important part of the World Food Program, as you might or some of you be familiar with. So our objective here is to maximize palatability. So we have R that are the ration variables encoding the amount of ration K for its commodity K, and we have some budget requirements, and we have some nutrition requirements. So basically, what we get at the end is a non-convex quadratic optimization problem over linear constraints. So by further taking the robust version of the problem, so assuming there is uncertainty in the nutrient coefficients beta, we obtain this new constraint here, which is a robust counterpart. And for some choices of Q, this can give us multiple conic constraints that are of interest. So in the generic form, our problem is formulated as follows here, as you can see here. And what is really interesting here is that, of course, if we have Q big equal to 1 or 2, this is sort of trivial, as is well known in the literature. But we can have Q being Q being something else, which gives us a power cone constraint. It is not that obvious. So in our problem here, we consider Q to be equal to. So we consider Q to be equal to 2/3, I think. Okay, so briefly to give you the results. So here, what we notice is that when we apply our RPT approach, again, we're able to solve the problem very fast and find a global optimal solution in this case, leveraging the multiplication of power cone constraints. And in one of the two cases here, Baran also could not solve it to optimality within 1 hour and turn something a little smaller. Remember, we have maximization problem here. Okay, so in summary, our RPT-BB approach, it can solve problems involving SLC functions, and sometimes faster than the state-of-the-art approaches. And it can scale up to problems with hundreds of variables and constraints. And of course, as Dike mentioned earlier, our main disadvantage is that we generate a lot of new variables and constraints because of all these multiplications. And this is the reason why it cannot scale to higher dimensional problems. But of course, on the other hand, it can handle a large class of non-convex optimization problems involving some of linear times convex functions. So those numerical experiments that I talked about are just a few cases that we can handle, but of course, our method is also applicable in multiple other problems. And of course, as I said, this is our main disadvantage is that it cannot scale to problems with larger constraints in the thousands or above. So this was pretty much it. So thank you everyone for attending the presentation.